Time just keeps on ticking. Today is the 16th. We should be working on some more chapter 5. We have 11 pages of chapter 5 left. So hopefully I should try to finish chapter 5 today. Our test closes today, but like I said, y'all, I'm like y'all. I mean, this is your last math class. A lot of y'all are uptight like me. You get your panties in a wad. It's okay. My sixth grade daughter's like that. She comes home some nights and she's like, Mama, I got this, dude. And she just breaks down. And I'm like, it's okay, baby. Let's just take one thing at a time. And she's like sick, nose snot. My bad, I forgot to put my phone on. She's sick, nose snotty, I can't miss school and I've got so much. You just don't understand, Mama. And I'm like, I've been there, it's okay. She hasn't missed a day of school in 3 years except the day my daddy died and we had his funeral. So, stuff happens, y'all. Y'all's kids get sick, y'all get sick. It's okay. Some other teachers don't realize that y'all have a life. But I'm one of those teachers that realize there is life outside of my class. So, it happens. So, it's not the end of the world that you don't take the stats class today. I mean, you got to take it. But if you need to text me and say, can I do it tomorrow? I'm having a crappy day. Or can I have to? It's okay with me. I mean, you got to do it. But if you're just overwhelmed, just let me know. Just go out there and make sure that I do it because I'm getting old and overwhelmed too and I may forget to do it. So just make sure that I do it. But 4 people have taken the test. 2 made an A, 1 made a B, and 1 didn't do so well, but she knew she wasn't going to do so well. So don't blame it off of her, okay? We had finished 5-1. We had done the majority of 5-2. In your homework, the homework problems are either going to say, use the 68, 95, 99, 7 rule, or it's not going to say that. So if it says in the directions to use the 68, 95, 99, 7 rule, then you're going to do either half of 68, all of the 68, 50, whatever. But if it doesn't say use the 68, 95, 99, 7 rule, then we're going to do that normal CDF thing that we did last time, which I'm going to do some more today. So, for this problem, I thought this was a cool problem. We all buy car batteries. And every time it seems like my car battery warranty just expired and then my car battery dies. So here is how the car battery people determine how long the warranty should be. So it says the car battery warranty is 36 months. If the breakdown times of this battery have a normal distribution with a mean of 46 months and a standard deviation of 8 months, determine the percent of batteries that can be expected to require repair or replacement under warranty. So the first thing I've got to do is draw my cute picture. I have a normal distribution. So there's my normal distribution. I have a mean of 46 months. I have a standard deviation of 8 months. And we're going to, our data piece, the piece of data that we know is 36 months. Now, is 36 going to be to the left or to the right of my mean? Is it below my mean or above my mean? Below. So it's going to be somewhere over here. Now, I don't have to do to the right, to the right, to the right, and to the left, to the left, to the left, because I'm not doing the 68, 95, 99, 7 rule. We good? Now, the question says, I want to know the percent that's under warranty. So if your battery is under warranty, is it going to be below 36 months or above 36 months? If it's under warranty, it's going to be less than 36 months. Your battery's going to need to be replaced less than 36 months. Y'all with me? You're lost?
No, that never happens.
That never happens. Because y'all, when is a battery company wants you to replace the battery under warranty? They don't, because they're paying for the replacement. So they mathematically, strategically chose for the battery month warranty to occur so that most people, batteries don't die under warranty.
You have to buy another one.
Amen. So, we want to figure out what percent of people actually get another battery for free. So, because they didn't say use the 68, 95, 99, 7 rule, that means we're going to do the normal CDF. So, we're going to do the lower limit, the upper limit, the mean, and the standard deviation. So what would my lower limit be? Where did I start shading on the low side? Low side. To the left, to the left, to the left. To the left, to the left, to the left. There's my low side on the left. What was the smallest number that I shaded? Negative 999. My upper limit is where I stop shading on the right. 36. What is my mean? 46. And what is my standard deviation? 8. So my lower limit is on the left. My upper limit is on my right. My mean and my standard deviation. So I go to my calculator. My normal standard deviation, my normal CDF is going to be second bars, second in the bars button. Number 2, normal CDF. My lower limit is negative 999. My upper limit is going to be 36. My mean is going to be 46. And my standard deviation is going to be 8. Oops, let me clear that out. Yes, ma'am? No, that's not the same thing. Just do negative 999.
You do second bars or just bars?
Second bar.
Second bars.
Go down to
Second
2.
bars go down to number 2, and it's negative 999. Yours was negative 1 times 10 to the 99. Yours was negative 1 times 10. So negative 999, 36, 46, and 8. Now, if yours doesn't have all those little spaces to fill in, then you're going to do negative 999, comma, 36, comma, 46, comma, 8.
Okay, so that was second bars,
Second bars.
number 2.
That's
Number
on our-
2, for normal CDF.
That's on our formula sheet, right?
The formula sheet's going to have all this crazy crap. Let me show you what the formula sheet has. The formula sheet has, open. The formula sheet, let me see if it has normal CDF out here. If it has it, it won't have all this stuff. No, I didn't even put it out there. No, your formula sheet does not have that. So you'll have to know that the lower limit is to the left, the upper limit is to the right, that little, now I do have on your formula sheet.
What did you say the highest to the right is the other day? Like the lowest is negative 999,
The highest is positive 999.
positive 99? Okay.
Yeah. The formula sheet does have, I think, the formula sheet does have, when that little symbol cursive U comes up,
Yeah.
that tells you that it's the mean,
hmm
and I think that's
There's
it.
another one too, like on our homework, another little symbol that means something.
Yeah,
I don't know what that, I don't know how to do that yet, I don't think.
yeah, we haven't gotten to that yet.
Okay.
So it's the left is the lower limit, and then the upper limit is the second one, and then the mean and the standard deviation. So when I pull that over, we whoop it, so that's 10.6%. So that means that 10.6% of the population get a free battery under warranty. So like Mariana says, ain't nobody usually getting a free warranty. battery. Almost everybody's battery dies after 36 months, which is why the battery company chose 36 months. Because what they did is they collected data and said, the average person's battery dies at 46 months. So we ain't gonna choose 46 months as our lifetime, because everybody will be getting a free battery. We gonna choose less than that. So they took all of their data and they found the average and they chose less than that, so they're not gonna give it to many people. Cool? All right, I did work it out pretty over here, and I even subtracted it from 100 to show you that 89.44% are not getting a free battery. All right, let's look at another one. I thought this one was cool. Try this one on your own. You know enough to do it. Draw the picture. I know, just breathe. This is a normal CDF problem. Who knew that men couldn't get into the Marines if they were too tall or too short? That's height discrimination. You got an answer?
Maybe.
That's what I got. You got an answer? That's what I got.
I feel like I did this really wrong.
Let me see. That's right. That's what I got. Look. You good?
No.
Let me see. Let me see. I love Marietta. That was with an accident. That's perfect. Anybody else want to give it to me? All right, so the first thing we're going to do, we have a normal distribution, which means it's going to look like that. We have a mean of 69. We have a standard deviation of 2.8. Our data, we actually have two data points, 64 and 78. 64 is gonna be over here, 78 is gonna be here. I knew that because 64 is less than 69, and 78 is greater than 69. And we wanna know the percent, that are eligible for the Marines based on height. And they're based on height between those two. So we're looking between those two data points. So it's gonna be the normal CDF. So we're gonna do the low and the high, the mean and the standard deviation. So the low is gonna be the one on the left, the high is gonna be the one on the right. So what's my low gonna be? 64, what's my high gonna be? 78, what's my mean gonna be? 69, what's my standard deviation gonna be?
2.8.
2.8. Okay, we don't have any negative 999s and positive 999s. A negative 999 is if I'm shading this. A 999 is positive 999 is if I'm shading that, if I'm going like to infinity. So when I go to my calculator, it's gonna be second bars, normal CDF. It's gonna be 64 is my left, 78 is my right, my mean is 69, and my standard deviation is 2.8. So this means that 96.23 or 96.2% of American males are eligible for the Marines based on their height. Now, I can easily say, if I come over here, I can do 100 minus 96.23. 100 minus 96.23. I can say 3.77% of American males are disqualified for the Marines because of their height. Isn't that cool? And the reason they disqualify you is because if you're really tall or really short, you should have a lot of health problems, like joint problems, knee problems, so you can't run, you can't like get into places or whatever that they have to do. So they kick you out because of your height. Okay, let me see if there's anything else I got going on. That's it for 5 point, whatever we were in, 5.2. So we really knew all of 5.2, I just wanted to do a couple more problems. No. Her question was, will we ever have a non-normal distribution? Not in this class. If you ever decide to take Math 120, then yes, you will do non-normal distributions. But in this class, it'll always say, given a normal distribution, the mean is this, the standard deviation is this, here's your 2 points or 1 point or whatever. Cool? Good question. Now, we are going to continue to do some of the types of problems that we've been doing, but I'm going to throw a new twist in it. This is 5.3. Up until now, we have been doing, this would be like 5.2, and now I'm going to be throwing in some new stuff, 5.3. Now, you know how I always explain things different than the book does. Here's another example. In 5.2, I either gave you 1 point or a couple of points. In 5.2, I just gave you 1 data point or 2 data points. So if I give you 1 or 2 data points, they call it in 5.2, they call it single data points, single data, individual data. And it may be 1 point or it may be 2 points. If I give you 1 or 2 points, it is what it is. Someone crazy's calling me. It is what it is. Okay, so it's like taking a picture. If I take a picture of 1 or 2 people, it is what it is. If they fat, you're going to see it. If they skinny, you're going to see it. If there's only one or two people in the picture, they can't hide much, right? It is what it is. Now, if I put a bunch of people in a picture, y'all, we're coming up on Thanksgiving, where we're going to have lots of people in a picture. You will never take a picture of your family again in a big picture without realizing when you take a big picture, that picture is going to look like a normal distribution. Think about it. If you take a bunch of your family and say, okay, y'all scooch in. The tall people you get in the middle. Now, come on, you stand on these either sides. What does that family look like? A normal distribution. How stinking amazing. Because you put the tall people and then you kind of bring them out. And the more people that's in the picture, you say, okay, y'all scoot in a little more because I can get y'all together. So like if you have 50 people, okay, scooting in, I can't get y'all on these sides, scooting in. So the bigger the group, the skinnier they look. I love taking pictures with a lot of people because we all scoot in. You know, people stand in front of you. So the bigger the people, the skinnier you look, or the smaller your standard deviation, the smaller your spread. So here, it is what it is. Your standard deviation is your standard deviation. Your spread is your spread. But here, your standard deviation, you may be 500 pounds. But if I put you with a lot of people, you're going to look this skinny in that picture. You with me? So, this picture, super easy to do. You stand up there, I take the picture, you're done. This picture is going to take me a little bit longer because I'm going to have to say, oh, you switch with this person, you kneel down. It's going to take me a little while. So we got an extra step with this person. So if it's group data, so if the problem is group data, we have an extra step. We have to redo the standard deviation. Redo the standard deviation. That's our extra step. We have to rearrange the people. So the process is the same. We just have one extra step that we have to do for the problem. So 5.2 and 5.3 are basically the same problem. We just have one extra step because we got to make the standard deviation skinnier because we got more people in there. Okay? All right. We good? So if there's only one or two pieces of data, it is what it is. If we have a bunch of data, the more people there are, the skinnier the standard deviation, and we got to redo the standard deviation because there's a bunch of people. This is called the central limit theorem. Let me just find a good problem. Okay, we can start with this one. Again, we're going to, I'll move this up a little bit so that I can just do the problem. This one says, based on data from the College Board, assume that SAT scores have a normal distribution. And what we just talked about a minute ago, everything we're going to do is a normal distribution. The mean is 1518. The standard deviation is 325. Assume that many samples of N are taken from a large population and that the mean of the SAT scores is computed for each sample. So they didn't give us the data yet, okay? So if I come down to part A, it says if the sample size is 100, find the mean and the If the sample size is 100, find the mean and standard deviation of the distribution of sample means. Huh. So, let me come down here. The mean never changes. Because y'all remember when I did several problems, I don't care if you're a skinny normal distribution or if you're a big boy, your mean is always going to be the same. Remember we talked about that, if you're skinny or if you're thick? The mean is always the same for a normal distribution. So my mean is never going to change. If I'm skinny or if I'm thick, my mean never changes. So my mean up here was 1518. No. Yes. I don't know why I wrote it down wrong here. My mean up there was 1518, so my mean down here is going to be 1518. My mean never changes. So I could have 1,000 people in my picture. My mean is never going to change. My mean is always going to be in the middle of the hump. Now, to redo the standard deviation, because we got to be skinny for those pictures of a lot of people. So because this is group data, because this is group data, right here, it even tells us we have a group of 100 people. There's 100 people in our picture. So we have to redo, we have to rearrange them in the picture. So here's the formula. My new standard deviation, my skinny person, is going to be my old person divided by the square root of how many people are in my picture. So, and I'm going to do a lot of these, so don't freak out on me. If I was alone, I'm 325 pounds. That's my old deviation. I'm going to divide that by the square root of how many people are in my picture. So it's going to be 325 divided by the square root of 100, because there's 100 people in my picture. So 325 divided by the square root of 100. So if I'm by myself, I'm 325 pounds. But when I'm with 100 people, I look like I'm 32.5 pounds. Because I got a bunch of people in my picture. You with me? So they only want two things from me. They want to know, if I put you in a group with 100 people, what is your mean? My mean doesn't change. And what is your new standard deviation? What are you going to look like when you're with all those other people? You're going to look like you're 32.5 pounds. So, this was the original problem. Here's my mean. Here's what I look like if I'm by myself. If I'm with 100 people, here's my mean, and here's what I look like. Let's look at another one. Here was my original problem. I got a normal distribution with a mean of 518 and I'm 325 pounds. But not only is 100 people going to be in a picture, but now we got 2,500 people in the picture. So what's my mean?
15.
It's still 1518. But now how skinny am I looking? 325 divided by the square root of 2,500. So 325 divided by the square root of 2,500. Now I look like I'm 6.5 pounds. Because y'all, if you put 2,500 people in a picture, you can't even tell who you are. You're so small. Does that make sense? The more people you have, the smaller your standard deviation is. The skinnier you look, the tinier you look.
So N, what is N?
N is the number of people in the picture, or the size of the group. Why is the standard deviation in part A different from the standard deviation in part B? The more people in the group, the smaller the standard deviation. Cool? Now, this is kind of showing you what I was talking about when you're going to do Thanksgiving and Christmas. If you just have, you know, like, this is me and my husband. My husband, this is like me, my husband, and my daughter. My husband's taller than me, I'm in the middle, and my daughter's not really now, but my daughter used to be shorter than me. Now, when I start putting, you know, my mama and my brother's family, it starts looking more normal. But then when I start adding cousins and aunts and uncles and grandparents, it starts looking more normal. And then when I start putting in neighborhood kids and extended family, and I put in a lot of people, it looks really normal. So even though it starts out skewed, the more people, like if I only talk 1 or 2 people, and then I go to 5 people, and then I go to 10 people, and then I go to 30 people. So no matter how it starts looking, the more people you add, it turns into a normal distribution. So like if you and your husband are the same height, and you add a couple more people, and then add even more people, and then add even more people. So if it starts out as uniform,